All right, let's see if we can find an electric field equation for this setup. So we're going to say we have a thin rod of charge and has some, say, total charge Q on it, has a length of L. We're going to be trying to find the field at this point P, maybe we call it E sub P, and we want it as a function of X. In our case, we're doing kind of a one-dimensional example because we're all in line, so all the charge, all the field will just be here. If we were up or down, we might have to do X and Y, but we're finding the total field and it's only in the X direction because of the symmetry of the problem. Okay, so how can we find the field at point P from this, maybe call it a thin wire, laying on the x-axis, basically. So that's what we're looking for. So when we're doing these problems, we have, at least for now, we're going to have a different method later, but for now we have to do an integral. So we're going to get a little bitty piece, a little dq of charge, infinitesimally small piece of charge here, all right? And we're going to find at point P the dE because of that little piece of charge, right? So the little bit of field from this charge, we'll use the superposition idea. Remember we had a bunch of point charges, we could just add up all the fields from all the different point charges. So it's the same kind of thing. We're going to have a whole bunch of tiny point charges all in a row here making up this line. We're going to add them all up, and that's how we do that is with an integral, right? So we're going to find the teeny little tiny part from one example, and then we're going to integrate over the whole length of our little wire here. All right, so we need first off to figure out what is the equation for our little dE. So it's a point charge, so what's the equation for electric field of a point charge? We had E is kq over r squared, magnitude-wise, and that's probably good enough for now. Remember we have E is a vector, and the vector is in the direction of the force, but we're all one-dimensional here. It's all just in the x direction, so we can just kind of just go with it. All right, so this is our general equation, but RQ is now dq, and so our dE is just k. dq is our charge divided by r squared. We'll leave it r squared for now. Okay, and so once we get our dE defined, then we're just going to integrate. So our total E is the integral of dE over the range from starting to ending, right? We're actually going to do some substitutions before we put in our limits so that we can figure out our limits of integration in terms of x. So, but this is kind of the end goal. We want to arrange dE so we can integrate it, right? Or we can just go ahead and just continue working here. So this is the integral of dE, so it's the integral of k dq over r squared. All right, so how can we need to relate, what is r? Can we simplify q, figure out something to do with our x, because we're really going to integrate, we really want to integrate from here to here on the wire. We want to go across the whole wire, add up all the charges, and add up all the fields from all the pieces of charge here. So we want to figure out equation for q and equation for r in terms of x, right? Because we're going to try to make x our variable of integration. So how can, or dq, how can we get dq in terms of x? Well, x, or probably actually dx, right? Because we're going to integrate over x. Okay, dq somehow related to dx. Well, we're going to use the idea of linear charge density. So lambda is what we call linear, I'll write it out I guess, linear charge density. So we're going to assume that it's a conductor. Conductors, the electrons, the charges can move freely over the surface, and they will spread themselves out evenly, trying to all get away from each other as much as they can, spread out, equal forces, because they're all the same size electrons, right? And so they'll be spread out there nice and evenly, and so it is the charge density will be coulombs per meter. It's a linear, we're just going to assume it's a straight line of charge. And so how can we get our lambda charge density? Then if we have the coulombs per meter, then for any length, then we can say that the charge is just the length times the charge density. All right, so yes, so we're going to say then that dq, how much charge do we have in a length dx, so many meters or so many pieces of a meter dx, right? dq is just going to be lambda dx, right? Charge density, coulombs per meter times the meters, we get the coulombs, which is what q is. All right, so what is lambda in this case? Well, like we said, lambda is coulombs per meter. We have a total of q coulombs over L meters. So in our case, lambda is going to be q over L. Q over L. 10 microcoulombs over half a meter, or I don't know, just some, whatever it happens to be. All right, so dq then is q over L times dx. All right, so we're going to take this and put it in for dq in a minute here anyway. How about r? Can we get r in terms of x? What is r in terms of x? What is r? In our equation in Coulomb's law and the electric field equation, r is how far the point is from the point where we're looking at the field, how far that is from the charge, right? So in this case, what is the distance from point P to our, this is our little dq, we have our little dx here. So how far is r? In this case, r is just x. Right, because we put P conveniently at the origin, so from here to here is just x. Right, that's our variable x. Good. All right, so now we can rewrite our integral. So E is just integral k dq, which is q over L dx, divided by r squared, which is x squared. All right, so E is, let's pull out the constants. Q is just a constant now, it's just the charge, total charge. L is the length of the wire, constant. K is coulombs, constant, it's constant. KQ over L, the integral of x to the negative 2 dx. Not bad, right? And let's see, but we do need some limits here. And so we will go from, say, start here and go to there. So we start at x is equal to d, and we go to x is equal to d plus L. Looks good to me. Okay, so how do we evaluate this integral? Well, we'll just do the antiderivative and put in the limits. So constant is out here. Antiderivative of x to the negative 2. When we do the antiderivative or take an integral, what do? We add 1 to the exponent and divide by the new exponent. So it's going to be 1 over negative 1, x to the negative 1, evaluated from d to d plus L. Okay, and so we're going to have, let's bring the negative out there, negative kq over L times 1 over d plus L minus 1 over d. Not too beautiful, no, is it? Do that right? I think I did. X to negative 1 is just 1 over x. Can we make it any prettier? We can, I guess, put the negative sign back in. So we got kq over L times 1 over d minus 1 over d plus L. I don't know if it was worth working out more. D plus L, get a common denominator here. D over D there. KQ over L times D plus L minus D over D times D plus L. Well, that's going to cancel. And so, and then the L cancels. And so we get KQ over D times D plus L. Okay, so going back to my first assumption, it's not a function of x, it's just the total EP at that point. I don't want it's not a function of x anymore because we're going over the whole rod, right? So we're not doing it for just a certain point. That's what this was, right? This was EP as a function of x, but we wanted to integrate over it. So a little bit off on that first equation there. So we just got E, magnitude only. Right, the direction is I hat. If we want the direction, we just put on there is just KQ over D times D plus L. Right, newtons per coulomb. So magnitude only, we got our E. Okay, let's stop there.